Hello there, Mr. Sutton here, bringing you the AB Calculus 6-9 Extra Practice number 3 solutions on accumulation problems. For this problem, we have a function f of t giving the rate of evaporation of water in liters per hour from a pond. T is the number of hours since noon. We want to know which of the following here gives the meaning of the integral from 4 to 10 of f of t dt in the context described. So since f of t is the rate at which water is evaporating, integrating that gives us the total amount of water that actually evaporates. So this is going to be the amount of water evaporated, and the 4 to 10, well, since t, the input for these limits of integration, is the number of hours since noon, this means we're talking about the water evaporating between 4 p.m. and 10 p.m. So looking at our answer choices, we have A, total amount of water that evaporates during the first 10 hours. Well, that would be pretty close to this, but that would be the integral from 0 to 10, not 4 to 10. So A isn't quite what we need. B, the amount of water that evaporates from 4 p.m. to 10 p.m., that is exactly what we said here, so we're going with choice B. And if you look at the rest of these, net change in rate of evaporation, well, that's going to be integral of f prime. And average rate of change, that's not even close. If that were the case, you would have like 1 over 10 minus 4 out in front. So yeah, definitely choice B is the way to go on this. For this problem, a home uses fuel oil at a rate given by this R of t function. And we want to know, let's see here, to the nearest gallon, the total amount of fuel used from time 0 to time 60. So to figure that out, we just have to take the integral of this R function from 0 to 60, which we can do on the calculator. And this is a calculator problem here. To make things a little easier on myself, I've entered the R function as the y1 in my y equals. And now quitting out of that, let me do math 9 to get my integral. We're going from 0 to 60. And I'll do alpha trace y1, put a dx over there, and let's see how much oil we used. About 820.655, and that's going to be gallons if we care about the units on this. So the closest answer choice would be D. For this one, we have the number of bacteria in a container increasing at a rate of R of t bacteria per hour. There's 1,000 of those little buggers in there at time 0. We want to know which expression gives the number of bacteria at time 3 hours. So to get the number of something, if you already have the rate of change and a starting amount, you have to take the starting amount, which is 1,000 in this case. So we've got 1,000 plus, now we have to take the change in bacteria from time 0 to time 3. To get that, we just integrate the rate of change, R of t, from 0 to 3. So this is the expression we need, and that's going to be choice D. For this problem, we have the rate at which rain accumulates in a bucket modeled by this R function. And let's see, this is milliliters per minute. T is measured in minutes since the rain started falling. How many milliliters of rain accumulate from time 0 to time 3? We have the rate of change of the rain. We just have to integrate that now from 0 to 3 to figure out how much rain we've accumulated in that time. So I'm doing integral then from 0 to 3 of 10t minus t squared dt. And since this is a no calculator problem, I'm going to have to use the fundamental theorem and do this one by hand. So taking my antiderivative, this first exponent bumps up to a 2. Dividing by that, I have 5t squared. This next one bumps up to a 3. Dividing by that, I have minus 1/3 t cubed. And that's from 0 to 3. So I've got all of this stuff with 3 plugged in, minus all of this stuff with 0 plugged in. Well, everything with a 0 is just gone. Over here now we have 5 times 9, that's going to be 45. And then we've got 1/3 times 27, which is just 9, so we're subtracting 9. That gives us a grand total of 36 milliliters of rain, which is going to be choice C. For this problem, during a 5K, we have runners passing a viewing stand at the rate at which they pass this stand over a 16-minute time interval is modeled by the R function. So R is a rate of runners, and that's actually graphed up here. So we just want to figure out basically how many runners pass the viewing stand between time 0 and time 16. So to figure that out, we're going to need to integrate the rate at which runners is changing. So we need the integral from 0 to 16 of r of t dt, which, since we have a graph of this thing, we just basically need to find the area under this curve. So we've got, let's see, 1, 2, 3, 4 different shapes we're going to have to add up here. The first shape is a rectangle from 0 to 4. So we have a base of 4 times a height of 40. And next we have a trapezoid. We have a base of 6. Actually, no, we're going to have to do a sideways trapezoid. So we have a base of, let's see here, 40 plus a base of 20 all over 2 times a height of, from 4 to 10 is 6. So that's our trapezoid area. And we'll calculate all of this and simplify it in a minute. I'm just getting the setup here. Next, we have another trapezoid from 10 to 12. This one has a base of 20 and a base of 50 that we're adding and dividing by 2. And then again, we're multiplying by that height of 2. And then finally, this last thing is a rectangle from between 12 and 16. So that's a base of 4 times a height of 50. Okay, time to simplify all this. So we've got 160 plus, well, let's see here. 6 divided by 2 is 3. 3 times 60 gives us 180. Over here, the 2's cancel. 20 plus 50 is 70. And 4 times 50 is 200. So let's see here. Just go left to right. We've got 340 plus 70 is going to be 410. Plus 200 is going to be 610. So we have 610 runners over the course of this race, giving us choice C. For the setup on this calculator-based free response problem, we have the temperature of water in a tub modeled by a strictly increasing twice differentiable function W. W is measured in degrees Fahrenheit, T is measured in minutes, and at time 0 we're told the temperature of the water is 55 degrees Fahrenheit, which seems kind of chilly. So the water is heated for 30 minutes, beginning at time 0. Values of W of T for selected times for the first 20 minutes are shown here in the table. So these are all temperatures at different times. That's the setup. Our first task on this is to use the data in the table to estimate W prime of 12, and then interpret what our answer means in the context of the problem. Okay, so W prime of 12, that's the rate at which the temperature is changing at exactly 12 minutes. Now, since we don't know W exactly what it is algebraically, taking its derivative is impossible at this point. But if we can't get the instantaneous rate of change at 12, we can at least find the average rate of change over an interval that has 12 on it for W. So we're going to find a rock for W to estimate this value. And I'm going to use an interval, the smallest interval that contains 12. So the interval from 9 to 15 seems like a good one to use. So let me do W of 15 minus W of 9 all over 15 minus 9. So that's going to be 67.9 minus 61.8 all over 15 minus 9, or 6, however you want to write it. And we could actually leave it like this and just stick units on it. We don't have to simplify it, but I feel like simplifying. So let me go to my calculator here. So here we go on the calculator. I'm going to use my fancy fractions setup, alpha y equals, so I don't have to worry about parentheses. And then press enter, and 3 decimals will be fine. That's 1.017. And that's going to be, let's see here, we had degrees over minutes, so Fahrenheit per minute. And now what does this actually mean? Well, this means that at 12 minutes, we have to put the time interval in there, at exactly 12 minutes, at least based on our approximation here, the temperature of the water is rising at a rate of 1.017 degrees Fahrenheit per minute. Our next task on this problem is to use the data in the table to evaluate integral from 0 to 20 of W prime of t dt. So we can actually use the fundamental theorem on this. The antiderivative of W prime is just W. So we're essentially evaluating W from 0 to 20, which means we're going to have W of 20 minus W of 0. Again, this is just fundamental theorem with the antiderivative of W prime. Well, what is W of 20? In the table, that's 71 degrees. W of 0 is 55 degrees. So we have 71 minus 55, giving us a value of, let's see here, that's going to be, since we're just doing these output values here, this is going to be 16 degrees Fahrenheit. Now, what does this actually mean? We just found the total change in our water temperature in degrees Fahrenheit from time 0 to time 20 minutes. For this problem part, we're told that for 0 to 20 minutes, the average temperature of the water is 1 over 20, integral from 0 to 20 of W of T dt. Now, we already could have known that ourselves using basic calculus, but they gave it to us, so that was nice. They want us to use a left Riemann sum with 4 subintervals indicated by our table to approximate this. And then they want to know if our approximation over or underestimates the actual average temperature of the water over these 20 minutes. Okay, so let's actually find our approximation first. So we're going to have 1 over 20 times, and now we have to open a parentheses, and we're going to have 4 rectangle areas being added together, 1 for each subinterval. So I've got the rectangle going from 0 to 4. This has a base of 4. Now I have to pick the height of the rectangle, and choosing between the left and the right height here, since this is a left Riemann sum, we always go with the leftmost height. So I have a rectangle with a base of 4 and a height of 55, plus a rectangle with a base of 5, height of 57.1. So that we're multiplying those. And then I have a base of 6 times a height of 61.8 being added in there. And finally, base of 5 from 15 to 20 times a height of 67.9. You don't have to simplify it, but I'm going to because I've got a calculator. Give me a moment here. All right, so I plugged all that in off camera. Press enter, and it comes out to 60.79, and that's going to be in degrees Fahrenheit because this is average temperature. So we want to know if this is over or under the true value. Well, the key on this, whenever you're doing a Riemann sum, is to look and see if the function is increasing or decreasing. And based off of that and the type of Riemann sum, we can always figure out if we have an over or under approximation. So the key here is they said that W was strictly increasing. So if it's strictly increasing, that means it's strictly increasing on the interval that we're approximating over, the interval from 0 to 20. So I'm going to mention the interval in there for full credit. And since we're strictly increasing there, LRAM is known to under-approximate on an increasing function. So we can write that our average temperature, 60.79 degrees Fahrenheit, our approximation, is actually less than the true average value that they gave us up there. So this is just a fancy way of saying we have an under-approximation. For the last part of this free response problem, we're told that from time 20 to 25, so this is kind of the epilogue to what we've been doing, the function W that models the water temperature has a first derivative given by this W prime function right here. Based on this model, we want the temperature of the water at time 25. Well, to get this, this is basically fundamental theorem in action. Let's take the temperature at time 20, because that was our last known temperature. So that was 71 degrees. So this is W of 25 we're finding. We have our starting temperature of 71 degrees, plus we need the change in temperature from time 20 to time 25. So I'm going to integrate from 20 to 25 this W prime of t function that they just gave me. And I'm going to do this on the calculator now. So to cut down on my chances of making mistakes entering all of this, I'm actually going to store W prime as y1 in my y equals. Now be careful when you do this. Only the x should be inside the square root here, because here only the t was in the square root. You don't want to accidentally put the cosine under the square root as well. So just making sure that those are separate. And then I've got the cosine of 0.06 t, but I put an x in here. Let's quit out of that. So I've got 71 plus, we're going to do, let's see here, math 9. And we're going from 20 to 25. Let me do alpha trace and pull up y1 out of there. And I'll put a dx. This all comes out to about 73.043, and that is going to be degrees Fahrenheit.